Oh, welcome, and today, rather than sort of doing a tutorial, I'm going to be looking at the subject of fail safe. So let's have a look at this project that's on the desktop. So this is the project I have on the desktop at the moment. You can see I've got ESP-32 dev module at the top, one in the middle, and a little D1 mini down the bottom. And these three items are communicating between each other using a form of ESP-NOW, and they're basically sending instructions to each other to tell each other what to do. And you can see different LEDs are coming on, and this is the project I'm working on at the moment. There'll be some servos, and it's to do with model railways and how accessories are controlled, and it's a sort of a wire-free method that I'm working on. But of course, when you're building any kind of control mechanism, you've got to think about what could go wrong. If this goes wrong, will it fail safe? So let's look at something very practical to get the idea of what I mean by this subject. So from a practical point of view, this is a block of wood. It's a piece of old railway sleeper. Now, I do a lot of work on my car. My driveway is slightly on a slope. So when I lift the car up on a jack to work on the brakes or take a wheel off, I lift the car up, but I'm always concerned that it's going to fall off the jack, which is going to be pretty bad if I'm underneath it. So I place one of these great big blocks of wood underneath the car, lower the car down onto the block of wood, and I know that way it's not going to be able to fall through the block of wood. In other words, if the jack fails, it's going to fail in a way that I am safe. And that's what we're going to look at today when we come to considerations for our Arduino projects. So the first subject we're going to think about as a fail-safe is electricity, especially voltage. Now, when we are messing around with our Arduinos or our ESP32s or whatever, we're usually dealing with 5 volts, 3.3 volts, maybe we've got a 12 volt power supply, but there are certain times, certain components, this is one of them, where we really have to think. Now, it's a relay, very simple to use in our project, but of course you can connect this, as it says here, to 240 volts. Now the issue is, if we connect our project to 240 volts, maybe we're going to control a light or something with this, we need to make sure that when we're building our project that everything is connected correctly. Because one of the issues when you build a permanent project is you may know how it works, but does everybody else? So, you know, if you've put your connectors in here, if you look at a decent electrical connector, usually what will happen is as the wires come out of the screw terminal, there will be something that the cable wraps around so that it can't be sort of pulled out easily. Now, if you just connect up 240 volts like this and all of a sudden a child pulls it out the end, then it could be a pretty bad afternoon. So when we're thinking about voltage, especially if you are messing around with mains voltage, you need to really think about the risks involved, and have you thought about, if you like, is it going to fail safe? Even at 5 volts, things go wrong. Here is another Arduino. It's a nice genuine one. You'll notice it's got a bit of black insulation tape around it. This is an Arduino Jew. It's a little bit more expensive. You'll notice that has a bit of black insulation tape around it. Both of them are suffering from the same problem. It's not the black insulation tape, it's they don't work. They've been burnt out. This one was particularly annoying because I went and connected it up on something on a railway layout and I put the wrong voltage through it, and believe me, it lasted milliseconds. I let the black smoke out of it. And again, I've got another component here. This is DF Mini. I plugged in the wrong way round and I burnt that one out as well. Most of the projects that I've worked on they work successfully and I don't damage stuff, but annoyingly, and let's be honest, this was a pain in the wallet blowing up a dew, it is easy to get the voltage wrong. Another thing that can cause issues, and this is my old breadboard that appears in certain videos, you will see it is melted here. And that was due to something very simple: stepper motors. In fact, I think it was this beastie that caused the problem. This is a particularly big stepper motor with a great big reduction gearbox on it. Obviously, voltage, we think about, giving an electric shock, but once you start to run things at higher power, especially on your breadboard type scenario, sometimes, there's a little wiring system within here. If the connection isn't quite right and it starts to just sort of spark across, things can get very warm. So again, when we are building our finished projects, and if you are dealing with especially the sort of the bigger NEMA 17s and even the ones that are bigger than that, just start to think about, before you're laying out your various components, what surface have you got them on? That is why this is on a block of wood. I don't put it on a surface where it could catch fire. I know wood eventually will catch fire, but it's not going to happen quickly. If it was on paper or something like that and I got a short, it could easily catch a fire. So just think about voltages, especially in your finished project. If you're using a power supply, where is that power supply coming from? Can it short out? Can cables get pulled out? So that's the first thing we're going to think about with our projects. Do they fail safe electrically? Now I'm going to continue going through some of the fail-safe things, and I'm going to work through what I would call the external risks. These are, if you like, non-programming risks, and then towards the end I'll look at some of the programming issues. This is another sort of fail-safe issue. This is a fume extractor. Now this is something that I use when I'm soldering, and it sits there and sucks the nasty fumes off my soldering iron away from my lungs. Now that's fine for me to use on my desk. However, if you look at the back, it's just got an old computer fan, and when it's spinning I could stick my fingers in the back of this. And it's just one of those things, again, when you're building your projects, some of these projects, this item is absolutely safe when it's on my desk because it's just me using it. But I couldn't really say to my grandkids, oh, just use granddad's sort of fume extractor, because before I know it, someone is going to have their fingers in the back. Now with this, it's going to be painful if you catch your finger in it. Now take a look at these. So this is that big stepper motor, and it is a stepper motor with a massive gearbox on the end of it. I think it's about 60-to-1 or something. Now I just want you to look at the shaft on that. I think it's about 8mm diameter, and it needs to be 8mm to handle the torque that this thing puts out. Phenomenal torque. Get your finger in the way of that when it's turning and you are really going to know about it. This is another example of high torque. This is a piece from a model railway. It's a sector plate that I built, and this relies on a motor with a gearbox that then turns a shaft in here and moves the item backwards and forwards. Now I can tell you, when I first built this, I made a major blunder on this and I messed up the limit switch, and the torque on this was enough to literally tear the entire model apart as it smashed its way and tried to do a full revolution. And of course the danger was that if I tried to stop it, the torque on this thing, it's only a 12-volt motor on the back. It doesn't look very big, but when you've got 100-to-1 reduction gear on there, suddenly the torque on that becomes extremely high. So as you're thinking about moving parts, even an electric motor on your desk with a fan blade on it, put your finger in the way of that, it is going to hurt. So when you're thinking about finished projects, and when I'm talking about finished projects here, this isn't something that's on the breadboard. this is something that you are going to leave set up somewhere for a long period of time. You just need to think, who is going to go near it? Not just people, but pets, wildlife, all sorts. What is going to go near it, and is there a danger that someone can get themselves trapped by the item that you're dealing with? Now, the next bit we're going to talk about is power failure. Now, what you're looking at here is a model railway turntable. If I turn it over, it's driven by yet another stepper motor via a belt, and that obviously turns the item. Now, it's a little bit difficult to see, but under here is a photo interrupter, and as the turntable comes round, there is a blade that cuts across, and that indexes the turntable so it knows where to start. Now, when I programmed this, I got all the code running nicely, and for the stepper motor to know where it actually is, it needs to index. So what I did was, when I wrote the code for this, the first thing it does is it starts up and it indexes itself. Fantastic. Works a treat. Now, I want you to have a think about this. We've got the turntable running and I get a power failure. So let's imagine that the turntable is in this position. I've got a train that's coming onto my turntable and the power fails. What happens when the power comes back on? The turntable immediately tries to index itself. Now, that is not going to do my lovely train any good when it gets sort of dragged across the layout and possibly trapped between a building. Now, this particular project, you know, I've scrapped it because I'll build a better one later, but okay, it could have damaged one of my trains. But if you think about it, if I'd been working on that, if my fingers had been inside and it had suddenly started up, would have been a pretty nasty moment. So again, it's that bit, not just what's going to happen when the item is running, but just thinking about little things. If the power suddenly goes off and comes back on, what is it going to do? How is the item going to restart? On a later version of this that I built just for a traverser, what happens is when the project starts up, this doesn't move at all. It just waits until a command is given to move it to its first location, because if I'm running the railway correctly, I've obviously looked at what I'm doing before I press the go button, and I'm not going to tell it to rotate if there's something halfway over. So again, you know, that is that bit, thinking, if you like, from a fail-safe point of view, how is this project going to work in a safe way? Now, this next item I'm going to introduce, it doesn't happen too often, but when it does, it's completely baffling, and it is the subject of interference. Now, we have a servo here. Now, these are in a lot of the starter kits, the SG90 servo, and obviously you've got the lead. You either plug it into a PCA 9685 board, or you can drive it directly off your Arduino. And the way the wiring works, you've got a ground, a power, and a signal wire. And it's a PWM signal, so if you like, it's the equivalent of a square wave. Now, on my model railway, I use DCC control. And my wiring works. I use these twin wires, and through here is running about, 12 to 14 volts, and it's running a square wave. So think about, you know, almost like AC current, but instead of it being like a smooth curve, it is a jagged sort of square wave. And one of the things you tend to do when you're building your model railway, you like all your cables running nicely. So I've got my servo controlling something, and then I sort of strap this cable alongside these wires. And what happens is, of course, these things are all pulsing backwards and forwards in time, and they are producing an electromagnetic field which was strong enough to actually generate a signal within the servo cable. And what I was finding was that I was having these servos, as I was sort of doing nothing, all of a sudden they'd just start twitching and jumping all over the place. And I had one of them actually basically destroy itself in the item that it was attached to, and that was all caused by electrical interference, crosstalk I believe they call it. And it's just one of those things that when you're building a project, something like that may not come to mind immediately, but it's a case of remembering where are the power cables running and where are the signal cables running. If you've got something that's got never end a signal, especially like these where they're changing at a pretty even basis and there's a lot of them together, that can actually cause a huge amount of electromagnetic interference. In fact, bizarrely, very often things like current monitors are actually work by wrapping basically the cables in a loop through I think it's an iron core, and they're actually picking up the signal to actually work out the current within the item. So as you can imagine, it's quite possible to generate enough crosstalk interference to affect the signal going to other items. So again, just thinking about that fail safe, have you thought about electrical interference? Now the next thing I want us to think about from a fail-safe point of view is wire breakage. Things break, especially in use. Now here we've got some limit switches, and usually in our Arduino project when we're using limit switches there will be a pull-up or a pull-down resistor that goes with it. Now here is a weird one. If we are using a pull-up resistor, then what we are saying is the default state is that power is running and the switch is switched when the power goes low. Now if you can imagine, if the wire broke and you're using a pull-up resistor, so let's imagine what we're then saying is when the switch gets pressed, the line goes low and then our motor starts to turn. Let's imagine now that we break the wire and all of a sudden the line has now gone low because the wire broke, not because the switch was pressed. So at that point our system is going to start turning and we have absolutely no way of stopping the item. Now that is an example. I've got a machine that I've built for my son that puts plaster into bags. That has a foot switch on it, and again that has a pull down resistor to make sure that you have to press the switch and power has to go through the switch. So if you like, the line has to go high for the machine to run. So if we were to damage the wire, it wouldn't make any difference. The machine just wouldn't work. But there are other occasions where actually you may want to know that you may have, for security reasons, power has to be on all the time, and if it goes low then you know you've got a problem. So again, when you are thinking from a fail-safe point of view, do you need pull-up or pull-down resistors? That will really depend on the situation that you want the unit that you are working on to fail safe in. So just an odd one to think about. So for the next item that we're going to think about from our sort of fail safe point of view is environmental issues. Now by that I don't mean saving the planet, it's more about saving your life or saving from injury or breakage, but things in the environment around your project. So for instance, dust, humidity, the weather, vibration, heat, light, all of these things can have an effect. So for instance, these limit switches, they are commonly used, but they're indoors. I'm not sure how that would survive in an outdoors environment with muck and water getting thrown all over it. It's the same with this ultrasonic sensor. Nothing wrong with an ultrasonic distance sensor, but this ultrasonic distance sensor has exactly the same sort of features as the one that we tend to know. This was at the HC SR04, but this one is more like the type that you see in the back of cars in their sort of reversing sensors. These are waterproof. So again, sometimes it's not so much a case of the wrong type of sensor, but finding one that is designed to work in the conditions that you're going to use the sensor. The same here. We've got a movement sensor, PIR sensor. I've used these on one of my cat detector projects. The issue that I had with it was sunlight would often trigger it. So what I had to do in the end was put a tube over the end of the sensor so that it blocked out any light that was sort of coming in from the side. All of these things are just little things to think about. The other bit on my cat detector project, let's be honest, it squirted water at cats if they walk by. They don't come in my garden anymore. Didn't want to harm them, but again, one of the issues that I had to think about from an environmental point of view was don't run the pump when it's freezing. Not because I was worried about squirting cold water, but if the water has frozen in the lines or in the pump, trying to run the pump would have destroyed the project. So it meant not only did I have to have the movement sensor in the project, but I also required a temperature sensor to make sure that the, if you like, the environment that the unit was running in was safe for all the components to work in. And again, that's one of those little things about fail safe. Is the sensor that I'm using the right one? You know, I like photo interrupters, but completely useless in a dusty environment. For something like that, you'd want something like a magnetic hall sensor. So again, it's that bit thinking about the environment that you're going to run your project in. Is there something, you know, silly things, vibration. Is vibration going to cause the wires to break? You know, if you keep wobbling this wire sort of backwards and forwards, eventually it will break. The same with connectors. When you're using your connectors, are you using the right ones? And I'm going to look at connectors next. So, human error. Well, human error is when someone uses or does something to your project in a way that you didn't expect. You know, I used to develop software for a company and I used to have testers, and I remember the one day one of the testers just leaning on the keyboard and the bit of software that he was working on instantly crashed, and he went back to the developer and he said, "That's a load of rubbish." And the developer said, "Well, you pressed all the keys at the same time. No one's ever going to do that." And he says, "Well, what happens if someone drops something on the keyboard?" And as the boss, I failed the project. And it went back and it was rewritten to take into account that people do stupid things. And nothing is idiot proof because idiots are ingenious, but we have to try our best. So this is a board shield that I built for my bagging machine. It puts powder into bags, and the way that the machine works, it has a motor that requires a clutch obviously for the drive, and when we want the system to stop, because it stops after it has moved a certain distance, it has to slam the brakes on. So both the brake and the clutch are the same type of unit. They both use 2 wires, but you'll notice one has a 2-pin connector, the other has a 3-pin connector. That's deliberate. One of these pins isn't used on the clutch, but the reason is that if you had to dismantle the machine and put it back together, if you plugged these in the wrong way round, when the machine started up, I can tell you it would be pretty catastrophic, and the bill is going to come to several £100 in the first 2 or 3 seconds. So that is why those plugs have separate pinouts. You'll notice here I've got 2 serial connectors. One goes to a set of weighing scales, the other goes to a touchscreen. Now they've got the same wiring configuration, same wiring colors. I have no problem, because if someone plugged those in back to front, it will cause absolutely no damage at all. It'll be absolutely obvious they've made a mistake because the scales won't work and the screen won't work. Piece of cake. But here you've got the power input. Now the power input, I've got 5 volts, 8 volts, 7 volts and ground. I know those sound quite specific voltages, and they are, because it is a very odd unit. You can't quite see it, but it's a 5-pin connector. I only need 4 supplies. And the reason it's got 5, these are 4 pins. So I wanted to make sure that there was no risk of someone plugging this into this. So each of these items has its own pin out. There's wasted pins, but it's all about the fact that someone cannot plug something in the wrong way round. Whereas the foot switch, let's be honest, it's a wire that goes down to a switch. And again, it's that it's held low, so the switch only activates when you press it. It goes high. It's got to be pressed. If the wire broke, if this cable got pulled out, the machine will not accidentally start. The other thing with the connectors that I've used here, they not only are sort of pretty good when it comes to vibration because they clip in. If you think about sort of a lot of the connectors that we use, they just sort of push on. Not good in a high vibration environment. Again, something to think about. And because of the way these clip in, they cannot be put on back to front. They only fit one way. Now, there's a link on the Digital Town website to a tutorial I did on connectors, but it's just something worth thinking about when you're building your project. People are going to do things with your project. They might be putting it together. They do not have the knowledge that you have, and you just need to be aware of that when you're designing your project. Think about the fact that people will use your project, they will spill things on it, they will knock it over, all sorts of things. Have you thought about, if you like, the fail-safe in those eventualities? Now, this next bit that we're going to look at, this is when we start to look at our programming and our programming ability. Now, in front of us we have a picture of a motorbike. What is it? Goodness knows. Lex Moto. No idea. Just picked it off the internet. I have had 2 people contact me for help with the same idea that they've had, and it was to do with their motorbikes being stolen. And what they wanted to do was attach some magnetically operated device that would, when the power is turned off, puts a bar through the wheel so that the motorbike can't be stolen. Then their idea was, up here they would have a keypad or a security fob, and when they came to their motorbike they would enter the key or put the fob near it. The magnet would then pull the bar out of the wheel and they would drive off. And they thought this was a really good idea, and they were asking me for help, and I was just like, oh my goodness, what are they doing? And my issue wasn't with the fact that you couldn't make it work, it was the fact that they hadn't thought about fail-safe. Imagine if it's using a proximity sensor, you're going down the road on your motorbike and it bounces out of your pocket, and at 60 mile an hour a bar goes in the wheel. Not going to be fun. Same thing, you're going down the road, and because it was using a voltage to pull the item out of the wheel, if you suddenly lost power, instantly the bar was going through the wheel. I was trying to explain to them that it would be far better to cut the ignition and for the vehicle to stop slowly without you going over the handlebars. So again, are you competent enough at this stage to build your project? I had another guy, he'd been learning Arduino for about 3 weeks. He'd controlled a stepper motor and he was working in a big factory, and he suddenly realized that he could automate a particular process using stepper motors that was lifting items that were nearly 10 tons in weight, and there were people moving around them. And I was sort of saying to him, I don't think that's particularly wise at your level of programming. Get a little bit more experience behind you so that you can fully understand what is going on. So when it comes to projects, you can have some great ideas and they can be great fun on the breadboard, but before you start throwing them into production, you really need to consider, where is your programming competency? Will your code fail safe? And that's the thing we're going to think about next. So when it comes to fail-safe code, I'm going to come back to this board and this brake and clutch. So imagine we've got a motor that is spinning, and when the clutch is engaged, the drive is engaged. So it's a bit just like a car. Your motor's running, you engage the clutch, and the motor is now connected to the drive system. And then of course you've also got a braking system. Now on this particular machine, you never want the clutch engaged while the brakes are on, because things are going to get very, very hot very quickly due to the speed the machine is running. So you need a process where you always release the clutch before the brake is applied. Now from a coding point of view, one of the issues that you can have, if you're not careful with your code, it's possible to have little bits of code to do with something like this all over the place. Now you'll notice here I have a function. I'm not going to explain the whole function, but what I want you to understand is that to stop the machine, I have one function in my code, and that function is always called when the machine is stopped. And there's a similar bit of code for when the machine is started. And this function is specifically to check that everything, the clutch is disengaged before the brake is applied. And again, when it goes in the other direction, has the brake been released before the clutch is engaged? And what I want you to understand from a fail-safe point of view is, if you have items like this that must be in the right order, try and make sure that they are all in one function, maybe two at the most. But if you like, write a very specific piece of code to deal with that safety critical item, so that as you make alterations elsewhere in your code, this always remains constant. That means you can test the item, make sure that it all works, and then once you've got it, if you like, that is locked down. That never ever gets changed again. And so as you're thinking about your code, especially things that can affect the safety of the machine, just think about, have you written your code not only that it fails safe as in it works, but is it written in such a way that if all of a sudden I edit something up here, is it suddenly going to destroy the order of items that affect critical items? Now, going back to the project on my desk, the final thing I want you to think about from a fail-safe point of view is testing. Testing is crucial, absolutely crucial. This project here, obviously I've got this ESP32 is communicating with this ESP32 and this D1 Mini. Now that's fantastic, that's all working. But what I've also got, there is another couple of D1 Minis. And what these are being used for, one artificially loads extra traffic onto the network deliberately, a really high volume of traffic, to make sure that the system works under a much higher load than I could ever imagine it using. Then I've also got this one here. This is used just to generate signal traffic in the same range, but that is nothing to do with this project. In other words, what I'm trying to generate with this is interference, as if this project was being run next door to another identical project? Will they interfere with each other? You know, that's part of the testing, because obviously if this is for a model railway layout and it's controlling the system, and I'm at an exhibition where someone else has got the same system, there's an addressing system in here. The idea is that they will not interfere with each other. But how do I know? How do I really know? And the only way to do it is literally to program up a board and just get it generating stupid amounts of traffic. As you can see, there's no pin headers, there's nothing on here. All it needs to be doing is just generating, if you like, signals, generating noise. Same with this one. It doesn't need to do anything. It just needs to send huge amounts of traffic on the system to make sure that these items still work correctly while all that excess traffic is going on. So when you start to think about testing, testing can take a lot of time. I was very fortunate to have worked down at the Ford Research Centre many years ago, and one of the things that amused me while I was working down there was they had a Ford Transit with the windscreen knocked out, and there was a robot turning the steering from one extreme to the other. And I was working down there about 3 months, and this thing was just running it stop to stop, day after day after day, until they eventually broke it. And they wanted to find out how many times they had to smash the steering before it broke. And that's testing. It's finding out, is that item good enough for the what I'm going to use it for? In other words, from their point of view, is the steering strong enough to withstand an idiot like me driving it? That's what they were doing. So again, sometimes testing, I've often done systems where I will actually program up I will take just a basic Arduino, and I will program it up to feed a signal to something. When I built the bagging machine, it has a sensor on there that sends signals through at high frequency. Now, I couldn't bring the machine into my workshop to test it, so I just took an Arduino and I emulated the signal, and I knew, if you like, the frequency of the signal that the machine would generate. So I ran my Arduino at about 4 times the rate, and the reason for that was to make sure that my code could handle all of these sort of interrupts that were going on without breaking into a sweat or missing any steps. So when it comes to testing, the good old breadboard, that's what it's there for. You play with it, but don't forget, think about, especially if you're doing wireless or Wi-Fi stuff, what else is on the network? What is going to cause interference? What is nearby? What's going to happen if the temperature changes? Car manufacturers actually have giant fridges and ovens that they run their cars in on rolling roads just to make sure that they work under different temperatures. So it's that idea that when you're building a project, before, if you like, you do your finished item, especially if you're going to start having boards made, make sure that you have absolutely nailed down everything and tested and tested and tested, and get, it might sound weird, someone who doesn't know how to use the project to test it. I did something the other day. I got my son, who really doesn't know about Arduinos and programming, and I got him to use one of my projects just to make sure that it was, putting it bluntly, idiot proof. Sorry about the coughing, got the lurgy at the moment. Anyway, I hope that's helped in giving you something to think about, thinking about how things fail safe, and especially think about switches and things to do with wires breaking. If something breaks, is this going to stop sensibly? Simple example, when you get a problem with your car, it doesn't just jam the brakes on. It usually comes up with a fault light and your car goes into limp mode. In other words, it's allowing you to safely maneuver to the side of the road and stop. And it's having that sort of same mental attitude when you're building your projects. Anyway, hope that's been useful for you, and I'll see you in the next video.